Good afternoon, everyone, and welcome to our second UNICA webinar in EUCAIM joint webinar. Today's webinar is titled Integrated Heterogeneous Real-World Cancer Data, the EUCAIM CDM and Hyper-Ontology for Semantic Interoperability. Thank you all very much for joining us. And today we are pleased to welcome three speakers: Elia Broggio, data scientist at Datrix; Dr. Valia Kalokiri, research data engineer at the Foundation for Research and Technology HELLAS, FORTH; Professor Oscar Pastor, full professor of computer science at the Polytechnic University of Valencia. Unfortunately, Michele Compare, our project coordinator, is unable to join us today, so his presentation will be delivered by his colleague Elia. Let's begin. So our agenda for today: we will begin with a short introduction to the UNICA project by Elia. And please note that we will finish with a Q&A session, so please feel free to write all of your questions in the chat during the presentations. Without further ado, I would like to give the floor to Elia.
Thank you, Julia. Thank you, everyone. Okay. My name is Elia Broggio. I'm a data scientist at Datrix, which is the coordinator entity of the UNICA project. In my presentation, I would like just to spend a few minutes to introduce you, or at least for those who are not familiar with our project, the main concept and the goal of the UNICA project. UNICA stands for Unified Network for International Cancer Advancement and is a co-funded project under the EU4Health program and is built in close collaboration with the EUCAIM initiative. But let's start with the problem we are trying to solve. As you may know, cancer is one of the leading causes of death in the European Union. In 2024 alone, we saw 2.74 million of new diagnoses and 1.27 million deaths in the European Union. And this number shows that there is a big potential to do better. In fact, in one end, we see that AI is rapidly advancing and is offering potential for better screening and early detection. But on the other hand, we still see that imaging data are still sealed. So we know that there are vast repositories of imaging data, but they remain isolated from individual hospitals. Of course, the European Union is well aware of this gap, and this is what the European policies are trying to bridge. In fact, AI is a key pillar of the European Beating Cancer Plan, in particular in the flagship number 2, which is the European Cancer Imaging Initiative. And the goal of the UKAIM project is to create a pan-European federated infrastructure of the identified cancer imaging data in order to support AI innovation, and the UNICA directly supports this effort. The main mission of the UNICA project first is to expand the European Cancer Imaging Initiative by adding a large-scale breast, lung, and prostate screening data from 12 medical centers. And all of them will reach Tier 3 integration, which means that we will be able to deploy federated processing within these centers. The second one is to align with the UKAIM, European Health Data Space, and other specifications in order to support standardized and verified imaging and clinical data. This will speed up and enhance the access for research and innovation. And the third is to pilot 2 AI models for cancer screening, and I will give you more detailing soon. To support this initiative, we have built a consortium of 16 partners from 10 countries. As you can see from the map, we span from the Azores Island to Ukraine, so we span across the entire width of Europe. We have 12 data holders, or 12 hospitals that will contribute directly to the UKAIM repository. And there are 4 technological providers, which are Datrix, the coordinator, UPV as alignment with the UKAIM initiative, Politecnico di Milano to help in the technical effort, and 81 watts for the dissemination and communication part. In terms of data, we estimate these figures. In particular, as you can see, we We collect cancer imaging from breast, lung, and prostate screening processes. As you can see from the bottom graph, breast is the main, most common cancer in women. Prostate is the most common cancer in men, while the lung is is second among the men and third among the women. And the final goal is to produce 2 deep learning-based models, one for the risk assessment of breast cancer from mammograms. The second one will be the detection of lung cancer from CT scans. And all using we will develop these algorithms using the federated environment provided by EUCAIM. This means that the data will never leave the hospital walls, but we will still able to produce a good result, nevertheless. And that was it for my brief introduction. I'll leave the floor to the next speaker.
Thank you very much, Elia. Now it's my pleasure to introduce our second speaker, Dr. Valia Kalokiri from FORTH. Valia, the floor is yours.
Hi, everyone. Hopefully you can hear me and see me. Let me see if I have gotten Yep. Have I? The control, yes, awesome. Okay, so yeah, hi everyone. I'm Valia Kalokiri from FORTH, and I'll present the EUCAIM Hyper-Ontology and Common Data Model that was actually developed together with the LIMIX team, specifically Mirna El Ghosh. Let's start. So before starting my presentation, I want to outline which were the requirements that the Hyper-Ontology and the CDM came to address. I don't know how many of you are aware, but EUCAIM actually originated from a great body of work from the AI for Health Imaging Network, the AI for HI, that consisted of these 5 projects you see on the right-hand side: the ProCancerEye, Chameleon, Incisive, EUCAIMage, and PRIMAGE. So these were 5 large EU-funded projects where the aim was to actually develop AI models in cancer imaging in order to solve unmet clinical needs. So what we came in the beginning in EUCAIM to address is to make all these big data repositories, that was a major outcome of these 5 projects, was to make them interoperable. What was the main problems that we had is that all projects, they were dealing with different cancer types. They were dealing with different clinical use cases, so different AI models that they had to be developed. And as such, because of the different use cases, they were collecting different clinical and different imaging data. Now, on the semantic aspect, they were all using different standardized terminologies and more specifically, also different levels of granularity on the information that they were collecting. In addition, different approaches on the imaging metadata. Actually, only one project standardized the metadata that were extracted from the DICOM images. Actually, all of them had DICOM images. Then different formats for the segmentation masks. Some were DICOM, but some others were NIfTI. And most importantly, the last point is that we're using, of course, standard data models, but these were different. So some were using OMOP and some were using the FHIR standard to represent their information. So what the Hyper-Ontology came to achieve is to achieve this semantic interoperability between all those cancer imaging repositories. So that was the first objective. And the second is, of course, to enable the semantic interoperability of the new individual smaller hospitals and smaller data holders that might either have also standardized data models in a way or totally ad hoc models, let's say in spreadsheets. So let's see a little bit in more detail what these projects were dealing with. So 2 of the projects, ProCancerEye and Chameleon, they adopted the OMOP CDM, which I'm sure most of you are aware. So regarding the clinical information they were storing, both of them they had a slight deviation from the standard implementation of OMOP. Why was that? Because there were some information that was not standardized in the OMOP vocabularies, so they had to have some local codes. And in addition, certain assumptions they had to be made regarding the model. And that, for example, was the dates. Most of the information existing in the individual hospitals did not have this information stored. For example, a specific procedure, we do not know when it happened, but also that was also the outcome of the anonymization approaches that had to take place in this project. So this information was actually missing. In addition, both of them use the oncology CDM extension of OMOP. And why is that? Because, cancer is a really complex domain. And in order to represent the granularity that is required to do cancer research, this extension is necessary for OMOP. And finally, you see the use case, all the data that was collected was use case based. Okay, then if we go to the imaging part, here things were a little bit more complicated because, as you know, OMOP does not have a specific dedicated, let's say, construct module for storing imaging related information. It can only store imaging related procedures, let's say. Okay, so it was until 2024 that they published the imaging extension as part of an imaging working group of OMOP. But during that process, ProCancerEye, that they actually, it was mandatory to store standardized imaging metadata for enabling querying and creating cohorts of specific patients. They introduced a radiology extension specifically for that reason, for standardizing imaging metadata, annotation metadata, segmentation, curation processes, and things like that. So both projects, both ProCancerEye and Chameleon, were using, as we say, an OMOP-like CDM. Now, if we go to the FHIR implementations, we have EUCAIM Image and Incisive that were both adopting HL7 FHIR for representing their information. Here, regarding the terminologies that were used, you can see that for clinical, for oncology, for therapies, there were various terminologies that were used, either individually per project or even within the same project, many different terminologies. And the problem we saw here is, again, that some terms are not standardized and they do not exist in any standard terminology. So what they did is they created a local dictionary, so they were able to represent that information. Okay, so we started, as we said, from this project with these thousands tens of thousands of patient cases, cancer patient cases, and we had to integrate clinical data and imaging data that were covering these 5 body sites that you see: the prostate, breast, colon, liver, lung, and rectum. All of them consisted of 16 different data sets. So you can see that for the clinical data, there is information about histology, tumor markers, staging, grading, comorbidities, family history, follow-up, and longitudinal kind of information. And in addition, for the imaging metadata, important metadata information extracted from DICOM, like the manufacturer, laterality, segmentation labels for imaging, all of these were available in the projects. So the important part here, as we said, is that all this information was either stored on OMOP or either on FHIR. So in EUCAIM, we had to address this challenge of the semantic and syntactic interoperability that comes from implementing these 2 different standards. However, what is important to mention is that these challenges do not just come from the fact that these two models are different, but we also found challenges of semantic and syntactic heterogeneity even within the same standard. So let's see an example of this just to understand a little bit better. So you see here on the top, I don't know if you can actually see my pointer. We have an example of the tumor marker test result. Okay, we are on the breast cancer scenario. So we have one project that uses OMOP. We have one project that uses FHIR. As you know, in OMOP, we have what we call domains. The domains in OMOP are the condition, the measurement, the procedure, etc., under which the standardized vocabularies are associated with. On the other hand, on FHIR, we have what we call resources, and then we have observations, procedures, etc. So the tumor marker test result of the estrogen receptor positive in OMOP, you can see that was represented as a condition. Okay, so it's under the condition domain by using a SNOMED vocabulary, and you see the code. On the other hand, on the FHIR, we do not have a single atomic concept as on OMOP. We have an attribute value pair where we have an observation. The estrogen receptor is an observation using a LOINC code. And the value was as a measurement value by using the SNOMED. So here in this scenario, we see both a semantic heterogeneity, but also a structural. Now, regarding the syntactic, sorry, the other example of the prostate, we can see an issue even within the same OMOP common data model. For example, you see the cancer staging. In ProCancerEye, it was again represented as one single atomic concept by using the cancer modifier OMOP standardized vocabularies. So you can actually see the method, the version of the vocabulary, the fact that it's the pathological metastasis category, whereas in another OMOP database, this was again as an attribute value pair, as a measurement and a measurement value by using different kinds of vocabulary, the NACCR, for both the measurement and the measurement value. Here we do not have information, for example, for the version or the type of the staging. I want to mention here that both of them are actually valid standard representations in OMOP. Okay, so here we see this kind of heterogeneity. Apart from this, we also found, as we said before, that some information was not standardized and as such is ambiguous. For example, in the breast scenario, the molecular subtype, for example, for those of you that know, luminal A, luminal B, triple negative, etc., is actually, we do not have any formal representation in any standard vocabularies, but to formally describe this in our case is important for doing our analysis, querying, etc. So as we said, what we developed this EUCAIM Hyper-Ontology to achieve this semantic interoperability between all those heterogeneous and disparate cancer imaging repositories. Also, apart from that, the EUCAIM Hyper-Ontology, as we say, it's application-based. So it has to be used in these three applications. For example, the first is on the federated querying. The second is to support image annotation or segmentation processes. And finally, to support the ETL process, to support the common data model. And in addition, we support the HealthDCAD AP implementation that is mandated by the EHDS, where we have an EUCAIM profile specifically for cancer imaging related information. Now let's see how we actually built that ontology. So as we say, we followed a hybrid iterative approach. You see here the steps. So first, requirement analysis and specifications, what we always do in software engineering. Then second, it's the knowledge acquisition. The third, the design and the conceptualization of the ontology. Fourth, formalize that using all, evaluate and validate our ontology. And finally, the maintenance. And this is a circle that keeps happening. So let's see each of the steps I just said in detail. The first thing is the requirement analysis and specifications. What we did here is that we developed this ontology requirement specification document, which is actually public available on Zenodo. What this document specifies is all the information that we got from the repositories is represented by using competency questions. It's something that we do in ontology development. And the purpose of this document was to specify the scope of the ontology, what's the kind of information that the ontology should support, and also the intended uses of the ontology. Now, the second step was this knowledge acquisition. What's the aim of this step is to align and map all the clinical and imaging knowledge that exist in the repositories with standard FAIR terminological and ontological resources. For doing that, we applied two kinds of mappings. The first are the label-based ones, and the second are the hierarchical-based ones. So starting with the label-based, what we did here is that we, through UMLS, Athena, the bioportal, and all the known biomedical ontologies, we tried to find synonyms of concepts, alternative labels, definitions of the concepts that existed. For example, you can see here the biopsy of prostate by SNOMED is an exact match, is equivalent to the prostatic biopsy from NCIT. This we have done for all the concepts that exist. And then the second type of mapping is this hierarchical based. Why we did that is to actually create the hierarchy of our ontology. How we did that? Using these ISA known relationships taken from the biomedical ontologies. For example, from SNOMED, you know, breast cancer is a neoplasm of breast. That's the broader concept, and the other is the narrower concept. And we go to the third step, which is our design and our conceptualization of the ontology. That, as you see here, we say it's a modular and layered architecture. Let's see what this means. So you see here at the bottom, we have three modules. The one is the clinical and biological module, the other is the common module, and the other is the imaging module. Why we have this module is to first of all, is the development of the ontology that actually is really big in size, and also have specific information, conceptual information in these kind of modules. For example, in the clinical biological, we have the pathological information, diagnostic information, biological molecular information, all these kinds of things. On the imaging, we have the information that relates to the imaging procedures and the metadata for them. And then at the common module, we have basically mainly the qualifiers from a MOP or the measurement values from FHIR, and specifically the grading and staging, not only, but also the grading and the staging information. So these are the modules. Then you see we have these layers. So we have the domain-specific concepts, so the domain-specific layer, the domain layer, the core layer, and the upper layer. Let's see now what these are. So the domain-specific, as it says, is all the concepts that are domain-specific. This is the information from the AI4HI projects. Then by using this ISA hierarchy, we go up the taxonomy where we now have the domain concepts, okay? So this is the approach, we call it bottom-up. We go bottom-up to build the ontology. Then we also have the top-down approach, that what we do, as we say, is that we ground the ontology into a core conceptual model. In our case, this core conceptual model is the M code. For those of you that do not know M code, I'll tell you in the next slide what this is. So this is our core conceptual model. And finally, we have these generic concepts that were defined by the participation of experts to actually generalize the content of the ontology. So now regarding M code, actually M code stands for Minimal Common Oncology Data Elements. It is actually a FHIR implementation, you can see here, intended specifically to show how to represent this complex cancer domain. And it was developed and it's owned by the American Society of Clinical Oncology, so from ASCO. As you can see here in the picture they have in their website, the M code has these thematic groups: the disease group, the treatment, the patient, assessment, genomics, and outcome. And each of these groups has specific kind of information. For example, for the disease is the cancer staging, the tumor characteristics, grading, and all this kind of information you see here in the orange. Then it has some health assessment related information. So health, patient's health before and during treatments, or before, for example, diagnosis or after diagnosis, like comorbidities, performance assessments, lab results, etc., etc. And of course, cancer treatments that they're actually split into three basic domains: the medication, the surgical procedures, and the radiotherapy. So what we did in our ontology is that we got this specification and we created the ontological model of it. As we said, this is the core conceptual model of our ontology. Here you see just an example. So the primary cancer condition that is specified has a finding site, a body location, the cancer patient is diagnosed with this condition, the patient is has undergone a surgical procedure, blah, blah. So associated morphology, the cancer staging, tumor markers, etc., etc. So the whole specification was actually modeled ontologically. Here, we go to that was the third step of the conceptualization. Then the fourth step is the formalization. So you actually see here just some screenshots of our ontology developed in Protégé. Here you see the taxonomy related to the clinical module. All the concepts in the clinical module have this code. All the concepts in the imaging module have the image prefix, and the qualifier ones have the com prefix in the top. So here you see the hierarchy, basically the classes, and here you see all the properties: object properties, data properties, annotation properties. However, apart from the taxonomy itself and the hierarchy, what is important is these mapping patterns that we have in the ontology. As an example, you can see here what we discussed in the beginning, the examples of the challenges, that, for example, the concept HACC, UICC, septum pathological M1A category in an OMOB is equivalent to the TNM path and has answered specifically this PM1A metastasis code. Okay. Similarly, for the HER2 positive, what is that equivalent with? So all these mapping patterns are really important. Now, following to the CDM, why do we have that CDM and how do we use it? So the EUCAIM CDM actually follows the conceptual model of the ontology, meaning the conceptual model of the M code model. We said it's a domain specific and it supports all the related cancer constructs explicitly. So our Hyper-Ontology supports the meaning of the data. Our CDM is about the structure of the data. And here on the bottom, you can actually see, as we say, we have actually semantically integrated these two constructs, the CDM and the Hyper-Ontology. As an example, in the CDM, the image series table and the attribute modality is equivalent in the hyper-ontology with the image series domain. The object property has image modality, and this is the range. So the range here, all the classes that are subclasses of these are actually the values that can be associated with this modality attribute in the CDM itself. So for representing that, we have actually created this EUCAIM Common Data Model Data Dictionary, where we have all the tables and the attributes, but we also have this terminology binding, which is really important to enable the semantic interoperability and the harmonization. So for each of the attributes, I don't know if you can see really well, but we have the binded property from the ontology, we have the range, and actually, because of this range of the ontology, all the permissible values, all the codes, the names, and all the different, here, you cannot really see, but here are all the terminologies that this concept is an exact match. So in EUCAIM, all our data sets are materialized based on this data model as we say, purpose-bound CSV files. And they will also be represented using the CSVW standard that is proposed by the Healthcare AP. This is important because through that, we also support the data minimization principle from GDPR, because as you know, we do not expose the whole data set of a data holder, but a subset of the data set that is actually requested by a data user. And now I want to go, I will go through two scenarios that I have, one about prostate cancer and another one on breast cancer. So here you have the information that was from the ProCancerEye project that was collected by ProCancerEye project. So let's see, there was a patient with had a PSA lab test and a digital rectal examination. The PSA was elevated and the DRE was positive. Then 22 days after, that's what we know, an MRI was performed, came up positive with a PIRADS of 5. There was a lesion of 10 millimeters maximum diameter, where it was in the right peripheral zone with this TN stage. Then after that, the patient went for a fusion biopsy that confirmed the cancer. They had a clinical stage. After that, they went for a prostatectomy. Look here that we actually do not know when this happened. We just know that the one happened after the other. So there was a prostatectomy. They came up with a Gleason 4+3, a volume, a diameter, then pathological TN stage, and the histology and intraductal carcinoma. And finally, after 6 months, there was a liver metastasis that was seen in the MRI and the PET. So how do we represent that? Don't get from here intimidated. What I want to show you here is how this information gets represented conceptually in the EUCAIM CDM. So we have specifically the PSAs as tumor markers. We have all the procedures that were done, and we know also the category of the procedure, if it's an imaging procedure, an evaluation procedure, a procedure on organ, etc., etc. These are concepts from the SNOMED itself. Then the cancer stages specifically represented, risk assessments like the PIRADS, the BIRADS, all kinds of RADS that is represented in cancer, and the grades, etc. Another important thing that I want to mention here is that you see by the colors that I have that, for example, the fusion biopsy is connected with this CT category, the MR gave this CT staging, or the prostatectomy, the Gleason, or the tumor that came up from the prostatectomy, or for example, the tumoral information that came up from the MR. And through that construct here, the tumor, we can actually see the evolution of specific tumors, for example, from 10 to 17, or if there is a difference in the tumor characteristics. The other important part is the imaging-related information. As I said, that DICOM itself for the values of specific tags, they are free text. And what we have done here at UNICA is to standardize some important information coming from the DICOM metadata. As an example, you can see here we have this image modality construct that supports the storage of modality-specific acquisition parameters. And for example, the slice thickness is standardized, tissue contrast, that is a T2 weighted. This is actually really important. It's extracted from the series description. For those of you that know free text, it's free text. So we are able to, through the ATL, to extract and standardize these things. I want to follow with the breast cancer. I will actually not stay here long. Similarly, we have a path for the breast, mammographies, biopsies, CTs, neoadjuvant therapy, mastectomies. Again, see here the times that, again, we don't know when things happen. We just have a relevance and an offset between events. And here again, it's the same representation based on this breast cancer-related information. For example, the fine needle aspiration of breast that happened came up with these tumor markers. So we are able to associate all the procedures, the conditions, the tumor markers, the stages where this histological grade came. For example, this one came from the aspiration of breast, etc., etc. And I want to conclude. I hope you are all here. So the metrics we have in the ontology, we are actually in version 2. We have more than 3,500 concepts. We have more than 2,000 exact mappings with different terminologies. You can actually see here all the kinds of terminologies that we support for each of the domains. We started with 5 cancer types. Currently, we support 22 cancer types. We do have information for these 22 cancer types. And we have various modalities. And finally, to conclude what we have achieved, we have this FAIR compliant Hyper-Ontology. Why it's FAIR? Findable, you can find it, it's accessible, it's interoperable, and it's reusable. And through that, we have supported the semantic interoperability and the harmonization across standards. And we have also established this common semantic layer in EUCAIM. And some future directions, as you know, this ontology needs continuous evolvement through expert supervision. And how we do that is by extending the ontology by integrating new data holders and new cancer domains. Of course, the challenges that can come up with this is the scalability and the complexity of the ontology. So its ontology size and it has complex relationships and complex patterns in the data. And finally, the sustainability aspect. Apart from these new data holders coming in, there are new terms, new contexts, the vocabulary, the standard vocabularies itself, they get updated. So the ontology needs to follow that. And here you can actually see some of the papers and what is already available. And with that, I want to conclude the presentation. Thank you. If you have any questions, you can email me or my colleague Mina that actually developed the ontology. Thank you.
Thank you very much, Vala, for the presentation. Our final speaker is Professor Oscar Pastor from Polytechnic University of Valencia. Professor Pastor, the floor is yours.
Okay, thank you very much, Julia. Can you hear me well?
Yes.
Well, I think that you have the control of the slides, so I will tell you when to change, all right? It's a few slides, so it's not going to be a hard task. Let me just focus this last part of the presentation in explaining the objective of UNICA as a reinforcement of what UCAIM is doing and what Valia was explaining us so clearly and brilliantly, because there is a huge work there. And I think that in UNICA we have several dreams. We want to be dreamers, and one of the very first dream is to make UCAIM very alive. I mean, to make UCAIM persistent in the future. So UNICA wants to accelerate, as you see here, the adoption and the expansion of the UCAIM infrastructure. by enabling secure, interoperable, and federated access to cancer screening data across Europe. And what we mean by that is that with UNICA, we have, well, beyond the dream of making EUCAIM persistent and endurable, is this idea of working together in the idea or even the dream of a European federated health system. And if we want to achieve such a kind of dream, we need data interoperability, as Valia was explaining very well. For that, and I think that this is the main goal of UNICA. What UNICA attempts to do is to address one of the main barriers, in particular in cancer research. And not only, I mean, we cannot talk about health in general. We focus on cancer and in imaging. But what we want to achieve is this idea of, fighting against the fragmentation of health data across institutions, countries, and data modalities. So this is very important because data interoperability and data integration and understanding data semantics is a huge challenge, especially in any domain, but especially in the health domain. So UNICA has born with this very strong goal and clear purpose of reinforcing the UNICA initiative. And if we go next, Julia, well, we see that in particular when we talk about data modeling and conceptual data and ontology engineering, well, it is true that UNICA is focusing on images. And when we want to have a mega, not metas, but a mega model of clinical data, we need to identify who are the main components of such a mega conceptual model. And well, in UNICA, we have the dream of integrating this four perspective under a holistic view, what we call the holistic conceptual model of cancer data in particular. Beyond the imaging data, that is the starting point, and this is where we are going to well, we don't start from scratch at all. We start from all the experience that UNICA is accumulating. We want to go further and integrating images data with all the other components that, well, Valia was already presenting in her presentation. We want to talk about genomics data, how to integrate genomics data with image data. But of course, we need the basic electronic health record data that are the basic data of the patients, and to complement all that information with a fourth dimension, that is the lab data. So what we want to have in some way is extending and going beyond what Valia was saying us. We want to have a holistic conceptual model that, oh, sorry, because the light was just switching off and I had to move for recovering that. Well, we want to have such an holistic conceptual model, and well, if we go next, Julia, we will see that there are very complex and different components of such a mega conceptual model of health data. In particular, well, this is a generic view of a conceptual model of the human genome that we use in our lab. Well, we are able to go from the DNA structure and from the identification of a variation to the different process that is followed when we go from DNA to a transcript to RNA to a protein, and from the protein to a pathway where we can, for instance, understand that if we identify a variant, this variant is just preventing the body from creating a transcript that should synthesize a protein that is not going to be created, and so a pathway that should use this protein is not going to work properly and home well. So as a consequence, we have, for instance, a tumor. So we make this connection between predictive AI and explainable AI that I will comment next. But well, this is just a view. If we go, we were looking at the genomic perspective, but this is, for instance, a preliminary instance of the medical imaging conceptual model where we have another component that is a view of this mega model, but that should be connected with the genomic perspective and also with the electronic health record and also with the lab data to give us this holistic perspective of clinical data that in UNICA we want to explore in depth, starting, as I said, from the imaging perspective. So this is why we go to the next one, Julia. This is what we mean by this second UNICA's dream after the first one that was making EUCAIM immortal in some way. We want to continue that, but we want to make it persistent in that direction through the creation of a holistic conceptual model of cancer data. And if we go next, I think that we enter the most interesting part of the challenge that I wanted to talk about. Because you all know that, when we talk about neurosymbolic AI is a hybrid AI paradigm that is combining the pattern recognition capabilities of neural networks and machine learning with the logical reasoning strengths that the symbolic AI has. So neural networks for learning from unstructured data like images, that is what UCAIM is doing, and symbolic AI to use explicit rules, logic for explainable and structured decision making that is a conceptual model based. So this is what we want to explore under the UNICA project. This is the third dream, to join and to combine predictive AI with explainable AI in such a neuro-symbolic AI, where we have on the one side we are able to identify patterns from raw data when we, for instance, from people that have or have not a given disease, we are able to identify what are the reasons that explain such a disease, and on the other side, explainable, the conceptual, the ontological-based perspective that is giving us the chance to explain why something that has been predicted by a neural network approach, well, how to explain why this is happening. So if we want to the next one, what we want to explain here, or what we try to do here, is to join this idea that in software engineering was just presented, and the combination of thinking fast and knowledge and slow thinking and knowledge. That is basically, thinking fast is the machine learning perspective, where we learn from raw data. Slow thinking slow is a theoretical, conceptual-based, ontological, grounded knowledge, where we make stable this knowledge that we have got from the thinking fast perspective. Well, this is the very last dream and challenge of what we want to do with UNICA, to make this combination by being sure that this holistic perspective dimension of health data give us the chance to have data that can be interpreted, understood, and explained when we talk about why a given disease appears in a human body. So just to conclude my short presentation of dreams and challenges in the next slide, I want to emphasize that UNICA is a brother sister project of UCAIM, and we have a very clear first takeaway that is that one, UCAIM is providing the common semantic framework that we want to explore, we want to extend, we want to understand and to make or to operationalize in the clinical health practice. So this idea, this objective, this purpose, this challenging purpose of UNICA is to operationalize federated cancer data sharing by strong use of conceptual modeling, by the strong use of ontology engineering, and by this application of we want to create a practical dimension of this neurosymbolic AI, where this predictive and this explainable AI knowledges are properly integrated. The last sentence is a crucial one, this multimodal integration that enables the next generation precision oncology because, well, we are focusing on cancer, image initially, but as I said, we want to go further and we want to make this multimodal integration in the sense that we want to integrate the four legs of the data universe that I was introducing before, where we have to integrate electronic health records, the data, what we could call conventional clinical data with imaging, with genomics, and with lab data in order to have such a, well, universal, holistic data manipulation system for clinical purpose that could lead us, well, I will finish with that dream of talking about a European federated health system that would strongly need such a kind of data integration. That is what UNICA, through the experience and the knowledge of EUCAIM, wants to achieve. Well, this was the main message that I wanted to transmit, and I thank you very much, Julia, for giving me the opportunity to make it possible.
Thank you very much, and thank you to all the speakers for the presentations. And we will now move to the Q&A session. If you have any questions, please write them in the chat, and we will be happy to answer them. Just let me see if there are any questions already. Yes, and we have a few questions from Johan. The first one is, how does the hyper-ontology compare to the use of upper-level ontologies such as BFO and SULO, or the definition of mapping using SOM?
Okay, that's for me. Thank you for the question. So the short answer is that all of them solve different actually layers of the interoperability problem that we have, and they do not compete each other. So the hyper-ontology that we have is, as we say, a domain semantic supports this domain semantic integration layer. Okay, these upper ontologies like the BFO, the basic formal ontology, or the upper level ontologies, they actually provide, let's say, the ontological foundations, which mean that they are actually domain independent, right? And they have these foundational semantics. They try to represent the world. What we try to do with the ontology is that our purpose is to, as I said, to have this unified semantic model. So one semantic model just for the oncology and the imaging domain. Now, regarding the standard for the mappings, for the representing the mappings, actually, in the ontology, we represent that using annotation properties. So through the annotation properties, we provide all the mappings between the different ontologies. And for example, syntactical mappings with OMOP and FIRE. I hope that this answered your question. And actually, just a small comment also, that our ontology is actually founded on BFO. We have represented the ontology using also Onto UML. If you can access the papers that I have actually shown in the slides, you can actually find more details about this.
Thank you very much for the answer. And we have one more question from Johan, and I think it's also addressed to Valia. By using M-code, grouping of information is based on the FHIR resources schema, while OMOP or Open EIHR are different again. Is FHIR seen as the target on the horizon to always map towards, or just because it is the most detailed described one?
Okay, that's a really good question. Thank you. So First of all, we do not, in EUCAIM, we do not force to have a FHIR implementation. We have used ENCODE not because of the FHIR implementation of it, but because of the oncological, the conceptual model of it, okay? So FHIR, in general, in my opinion, is often treated, as we say, the lingua franca for data exchange, but it's not necessarily the ideal semantic model that we would like to have, okay? So in EUCAIM, we use ENCODE for the, as I said, for the semantic, for the conceptual model of it. What is, though, important is because we use this ENCODE specification, a next step, if this information is to be exchanged, you can use the FHIR implementation of it. So FHIR is, let's say, one implementation of that. It can be also translated to a MOP. It can be translated to MOP vocabularies and things like that. So this is my answer for that. I don't know if I covered if you want to ask something more.
Thank you. And we have 2 more questions from Emily. Thank you for the excellent and thorough presentation and also sharing the citations associated with the work. Could you expand can you expand a bit more on the Health DCIT AP? Is this something which is essentially scrapped from the DICOM? Is there a program which EUCAIM has which make the necessary scrape?
Okay, excellent question as well. So regarding the Health DCAT AP, as I said, this is the specification that is required, and it's a specification by the EHDS. So all the data holders should represent their data sets by using this dataset metadata model. What is important to understand here is that this Health DCAT AP refers to aggregated level metadata. It's not individual. It's not about individual records. Okay, so through this Health DCAT AP, what we have, of course, it's a generic model. Okay, it's for the whole health domain. What we have in EUCAIM is that we got this Health DCAT AP and we extended it a little bit more to represent cancer-specific information and imaging information. And what I mean by that is that we would like our data sets to describe, for example, the fact that I have, a T2-weighted MR modality in this specific data set, or that I have an annotation on the prostate gland organ. So someone could actually query and find out, how many patients they have segmentation on this and that, or using that histology, or this kind of information. So we have extended Health DCAT with specific cancer imaging related metadata, but again, important to understand, it's on the aggregated level, not on the individual level. And then there was a second part, right, about the DICOM. You're right. We have, so through the ETL process that we have when we want to translate the data and standardize the data, we have a tool that extracts the DICOM metadata, and then through some mappings that we request the data holder to create, we map, for example, as I said, the example before, a series description that describes the T2 weighted. We can standardize that through the ETL process, but it's we need some help from the data holders.
Thank you very much. And as I anticipated, there's one more question from Emily. If I were to attempt to apply the Hyper-Ontology and CDM of EUCAIM to my own data set, how would you suggest I start?
Okay, another excellent question. So it actually depends on if your data is standardized or not. If you follow any standard model like OMOP, or if your data is represented in FHIR, because depending on what's your initial let's say, status, we provide different different ways, okay, different roads. So, for example, if you have just an Excel file, right, we recommend that you actually translate directly to the EUCAIM CDM, which is the representation that the data user will actually access and use for developing AI models or for doing federated processing. If there is an OMOP or a FHIR, let's say, repository, what we recommend is that you can always translate ETL from your implementation to the common semantics that we have in EUCAIM, but you can actually also create what we call a mediator. So you have a semantic layer on top of your databases that you can actually translate when a request happens. You can translate dynamically, let's say, the information into the common structure, and then that can be used with other repositories.
Thank you very much. Thank you very much for the questions, and thank you very much for the answers, Valia. And if there are no further questions, we will conclude today's webinar. On behalf of the UNICA consortium, I would like to thank you all to the speakers for sharing their expertise today, and thank all of you for joining us. If you would like to follow the project's progress and hear about future events, please follow the UNICA project on LinkedIn and visit our website. Thank you very much again, and have a wonderful afternoon. Thank you. Goodbye.
Thank you, everyone.
Thank you. Bye-bye.
Bye-bye.